Good morning, everyone. My name is Shakiba, and I will present our work on occlusion management techniques for Glanceable AR interfaces. So we will start by talking about the motivation behind this study. Then we will move on to introduce the solution we are proposing to solve the problem in hand. And finally, we will take a look at the results of our user study. As for the motivation behind this study, we mainly focus on defining what Glanceable AR interfaces are and discussing why occlusion management is important. So AR headphone displays are becoming lightweight and powerful, and soon enough they will be accessible everywhere. It's been long since AR have been predicted to become the future of everyday information access. Back in 2002 and 2003, Feiyu predicted AR to be much like telephones and PCs, displaying information that we expect to see both at work and at play. And Davari proposed AR being an AR desktop workspace. All of these provides the opportunity for easy hands-free information access through a glance. We suggest a few criteria for classifying AR interfaces, and then we define glanceable AR interfaces based on these criteria. We believe that AR interfaces can be put into different categories based on whether the virtual content is accessible temporarily or persistently, the number of the tasks that the user interacts with when using the interface, the content's relative placement, is it fixed to the user's body, fixed to the wall, and there's also the level of information detail to be considered. Is it concise or verbose? And finally, the level of focus. Is the content the user's secondary task, or is their central focus and their primary task? Now, as for the glassable content, imagine you're back in the good old days when you could leave your house. Imagine that you're walking down the street, going to a cafe to meet a friend, and you receive a text from them. And you want this text message to be accessible temporarily, and you want to access it with a quick glance while you're performing your other primary task, which is walking. So glassable AR interfaces are accessible temporarily. They present the content in a concise level of information detail, and they are as the secondary focus of the user in a multitasking environment. As for the placement, since they must be available at any time and place, they follow the user. With the rise of AR and glanceable content, we're building an environment in which real-world and virtual content coexist. And that makes it critical to detect and handle the occlusions between them, especially that these occlusions can affect the user's awareness and safety. One of the instances that drew the attention of general public to AR was the mobile game Pokemon Go. And yet it was the cause of thousands of car crashes and even deaths, mainly because the users lost their awareness of the real world and the virtual content was blocking their view of the real world. Or in a less severe case, you can say when you're having a conversation with a friend, you don't want any unwanted virtual content blocking their face. And so in this work, we're mainly focusing on unwanted occlusion of important real-world objects by virtual content. Next, we will talk about the techniques that we propose for dealing with such occlusions. We consider three technique dimensions for our technique design: content prioritization, adaptation mechanism, and automation level. For content prioritization, when prioritizing the virtual content, whether it's blocking the real-world content of importance or not, it will always be visible. On the other hand, if you're prioritizing the real-world content, no virtual content will occlude it. For the adaptation mechanism, the reposition mechanism raises the occluding glanceable content above the user's eye level to reveal the real-world content that was behind it. The translucency mechanism adapts the translucency level of the occluding glanceable content to enable the user to see the real-world object behind it. In our technique design, we included three automation levels. The fully automatic and automatic detection techniques both detect the occurrence of occlusion when glanceable content blocks the user's view of an important real-world object. Full automation uses an adaptation mechanism and automatically resolves this occlusion, but automatic detection provides a visual cue on the occluding virtual content to notify the user about the occurrence of the occlusion, but it gives the user control to choose whether they want to resolve the occlusion or they want to continue accessing the virtual content. Here we use the blinking red outline as the visual cue. The fully manual techniques don't introduce any distraction and give the user the absolute control, but this is at the expense of reducing the awareness of the surrounding real world. Here you can see the fully manual technique that uses translucency as its adaptation mechanism and prioritizes the real world. So initially all of the glanceable content are transparent and the user can manually decide to make them opaque. Here's an instance of the fully automatic technique that uses reposition as its mechanism. So whenever a piece of glanceable content is blocking the child, which is the important real-world object in our experiment, it will move the content up. And this is a list of the 8 different techniques that we designed. Combining the design dimensions that we had, our design space includes 12 unique techniques. However, 4 of these techniques, which were the non-manual techniques that prioritize the real world, were excluded. And that's because the practicality of such fully automatic context-aware interfaces requires more investigation. Next, we will introduce our experiment and show the results of our user study. We simulated a future world in which AR eyeglasses replace our today's smartphones. In the scenario, the participant is a babysitter. They are placed in a virtual room watching TV while 6 pieces of glanceable content, like weather app or email, are arranged around them. They were asked to perform 2 tasks: maintain awareness of the real world and access virtual information. To maintain awareness of the real world, the participant was asked to watch Kevin, an autistic child who would occasionally seek their attention by waving at them. So the primary task was to notice Kevin's wave and wave back at him immediately. To access virtual information, occasionally a question, say asking the temperature at a specific time of the day or number of unread emails, would pop on the TV, and the participant was asked to access glanceable content to answer the question. We conducted a within subject user study on 32 participants, and we had 8 technique orderings based on a Latin square. So we had 4 participants use each one of the technique orderings. We evaluated our techniques and technique design dimensions based on 4 metrics: user preference, how easy they find it to access information from the real world and from the glanceable content, their task performance time, and the number of times they clicked on the glanceable content when using each technique. From our participants, 84.4% preferred prioritizing the real world, 84.4% preferred translucency, and 93% preferred full automation. For the comparison of the techniques, all participants preferred one of the 4 techniques in which the child is initially visible. As you can see, 75% preferred one of the techniques that uses the translucency mechanism, and 50% choose the technique that uses translucency mechanism and prioritizes the real world as the best technique. Our participants ranked ease of information access on a scale of 1 to 5, with 5 being the easiest. The results show that translucency mechanism results in a higher ease of information, virtual information access. When accessing information from the real world, prioritizing the real world was ranked as the easiest by more than 85% of our participants. Also, full automation was perceived as the easiest compared to both of the other 2 automation levels. The techniques that made the child initially visible were ranked consistently higher than the other techniques. When accessing information from the real world, task performance time was not affected by any of our parameters. But when accessing information from the virtual content, in terms of adaptation mechanism, translucency was significantly faster. And task performance time was significantly different between different techniques. Pairwise comparison shows that the technique that uses reposition as the mechanism and prioritizes the virtual content that technique was significantly slower than the other techniques. For the average operation count, prioritizing the real world results in a significantly lower average operation count than prioritizing the virtual content. When prioritizing the real world, the average operation count for accessing information from the real world was approximately 0. As expected, the average operation count for full automation is significantly lower than that of automatic detection and full manual. And as for the techniques, it significantly varies amongst all of the techniques. In conclusion, our major findings indicates that full automation and real-world prioritization are preferred and perceived as easier when monitoring the real world. Translucency is perceived easier and performed faster when accessing information from virtual content, and it is the preferred adaptation mechanism. And just in general, our users in our scenario primarily cared about the visibility of the real world and minimizing visual clutter and information overload. Thanks a lot for your attention. If there are any questions or comments, I will be happy to answer them.